Hi Math 215 students. In this series of 4 videos, we're going to introduce matrix multiplication as a function and talk a little bit more about properties of those functions. So this will correspond to both sections 1.8 and 1.9. We may cover a few things with a slightly different emphasis or in a different order, but all of these 4 videos deal with those sections. Our outcomes for this first video are as shown here. You have a number of terms you'll want to be able to define. You want to determine the image of a given point under a given matrix transformation and determine whether a given point is in the range of a given matrix transformation, and if so, find the point or points in the domain mapping to it. Okay, so to this point in the semester, we've seen 3 big perspectives for looking at the same problem. So we first started off talking about systems of linear equations where you might have 1 or 2 or 3 or many linear equations looking like this. We then talked about how to express a system of linear equations like a vector equation. So here you're trying to find the coefficients x1 and x2 that make the left-hand side equal to the right-hand side. And then the third perspective was the matrix vector equation, where you have a matrix times a vector equal to another vector. And the idea is, can you find out what x is to make this equation true? Now, the first 2 perspectives, maybe you understand the usefulness of these. You might be wondering at this point why we might need the third perspective. And we'll try to talk a little bit about that. And what we'll do is we'll kind of tie the left-hand side of this equation to the idea of a function that you've run into before. So let's go back in your memory or your imagination. Let's remember what it was like at the beginning of algebra. When you first saw algebra, you were probably introduced to properties of numbers and you reminded of some facts from arithmetic. But pretty quickly on, you were introduced to this idea of a function. A function is a rule that takes an input value and produces an output value. All right? Now, you probably saw a drawing like this, some kind of box or whatever to represent this function. The function can be any rule at all you want as long as for each input that's allowed, there is exactly one output allowed. Now, as you went on, you talked about functions given by equations. And so if you were to look at f of x equals x squared minus 4, what we would do is plug in an x in for our input value, and the f of x would tell us the output value according to this formula. So if I were to put in x equals 3, for instance, where we get f of 3 is equal to 3 squared minus 4, which is 5. And if you take a look at the graph on the right, you see that when x equals 3, y is equal to 5. And the graph here, the graph of this parabola, illustrates the values that you get out from the function x squared minus 4. Now, there were a couple terms that you ran into when you first saw functions. You were probably introduced to the idea of the domain of a function. And the domain is the set of all the possible or allowed inputs. So for this function written out here and drawn here, without any further information given you, you might just assume that the domain is everything that's possible to plug in for x, and it's possible to square any possible real number and subtract 4 from any possible real number. So you might say that the domain is the set of all real numbers. Now the range, on the other hand, is sometimes known as the image, and in particular in linear algebra we might refer to the image and the range interchangeably. They're synonymous. But the range or the image is the set of all the outputs that ever happen when you plug in all the possible inputs. So we're looking at all of the numbers that are ever spit out by the function. And for this example, if you take a look at the graph, the range corresponds to all the y values that ever show up on the green graph. Now the y values include all the real numbers from -4 onwards, but we don't ever have a y values output that is less than -4. And so we might write the range as y greater than or equal to -4, or if we wanted to write it as an interval, we might use the interval notation -4 infinity with a closed bracket around the -4 to indicate that -4 is part of the image or part of the range. All right, now hopefully that's familiar to you in some degree. We are going to think back a little bit more, and in algebra and later classes like calculus, you moved further than that, right? Once you had identified functions, what they are, and once you were familiar with a couple of basic functions, then you started talking about things like the intercepts of your function, where it crosses the x-intercept or the y-axis, the y-intercept. You talked about zeros and roots of functions. You talked about end behavior, what happens as x goes to infinity or minus infinity. You talked about factorizations of certain functions. You talked about taking the limit of a function at a place, finding the derivative or the slope of a function at a place, and finding the integral or the area between the curve and the x-axis over a certain interval. All right, so keep that in mind. When you first entered algebra, you learned about functions, you learned about domains and ranges, and then later on, you learned other things about functions. We're going to follow somewhat of the same trajectory as we talk about matrix functions. And so here we're going to define a type of function coming from matrix multiplication. We will call it a matrix transformation. And a matrix transformation is any vector function having the form t of x is equal to a times x, where a is some m by n matrix. All right, so as an example here, down below, if t of x is this matrix times x, then you can see that what I'm supposed to do is if I have an input vector like 1, 1, I'm going to multiply it onto that matrix, and whatever the answer is, this matrix times that vector, that will be what the output is for my matrix transformation. So because this is a rule that gives us an input and spits out an output, it is a function. And as you take a look at it, if we were to actually multiply the vector 1, 1 onto this matrix, you'll see that you're going to take 1 times the first column plus 1 times the second column, and you end up with the vector 8, 2, 7. So for our input of 1, 1, our output is 8, 2, 7. Our input involves vectors from R2. Our output involves vectors from R3, actually, because of the shape of this matrix. Okay, so what would the domain be? Well, the domain is the set of all the vectors that you are allowed to plug in. And as you take a look at this matrix, for which x does it make sense to multiply this matrix by x? Well, in order for the multiplication to be defined, you need to have 2 entries because there are 2 columns, and matrix multiplication needs those numbers to be the same. So, which vectors have 2 entries? Well, all of them do if they come from R2. Okay? Now, what is the range? Now, this is a slightly more tricky question. We do know that the range includes vectors from R3. Maybe not all the vectors, but at least some of the vectors from R3. And actually, no matter which vector you multiply this matrix by, if the vector comes from R2, you're going to be left with a vector from R3. However, we don't know yet that the range is all of the vectors in R3. And so it's possible that the range looks a little bit like this picture. If you can imagine that the set of 3-dimensional space is indicated by that box there, the range may actually just be a sort of a subset of that space. It may not include everything in that space. It may just include a slice of that space. All right, so in general, finding the range or the image of a matrix transformation can be a little bit more involved than finding the domain. What we can say right away, though, without thinking too much, is that the range is a subset of R3. Okay, now, if we wanted to be a bit more precise, what we're going to say is that the codomain of this function is R3. So the codomain is defined as a set to which all of the output values are expected to belong. So remember, when we started with our definition, we said that when you multiply this matrix by a two-dimensional vector, you're going to get out a three-dimensional vector. And so that would tell us that our codomain would be R3. R3 is sort of the universe that our output values belong to. Now the actual range, the actual vectors you get from R3 may just be a certain small subset of R3, but we can say that the codomain is R3. And so this will be a handy tool for us. We can say something about the output. We can call it the codomain, even if we can't specify exactly what the range is just yet. Okay, now here's a bit of notation to make this clear to other mathematicians. What we often do to convey the transformation name, domain, and codomain of a matrix transformation, we often write the name of the function t colon Rn to Rm, where Rn is the domain. This is a right-handed pointing arrow, and Rm is the codomain. So you can see here that the domain is listed first. That's where the inputs are going to come from. And then this arrow kind of represents the action of that function, and it spits out elements from the codomain Rm. Okay? Now, when you see this written in process, it's often that you see both of these things kind of appearing in the same sentence. So in the example that we've been working with, we would say that the function t mapped from R2 to R3 is defined by t of x is equal to the matrix times x. So you'll notice that we use that notation when we first mentioned t. We're just specifying up front its domain and codomain, and then we get into the details of what t of x actually equals. All right, this is sort of a pattern of the speech of mathematicians, but it's worth noticing. You'll notice it in your textbook many times, and it might be a good idea to practice writing it yourself. Let's go to an exercise. Let's suppose that t of x is defined by this matrix times x. Let's see if we can answer first the domain and the codomain of this function, and then we'll move on to the second question. So, to talk about the domain of t, we want to look at which values are allowed to be plugged in for x. What kind of vector can x be? And as you take a look at what would have to happen in order for you to do matrix multiplication, you'll see that because there are 3 columns here, we're going to need to have 3 rows in x. And so the domain of t will be R3. And then when we do that matrix multiplication, we multiply this 2 by 3 matrix onto the 3 by 1 vector. What we'll be doing is taking a linear combination of these columns which come from R2, and so the linear combination, the answer, is going to end up being in R2. So the codomain, we could say, and we should say, is R2. Okay, please take a look at that. It is always the case that in a matrix transformation, the number of columns gives you an idea of the domain, and the number of rows gives you an idea of the codomain. Now the second question on the slide is 7, 1 in the range of this linear transformation? We know that the codomain is R2, and 7, 1 is a vector from R2, so there's a possibility that it's in the range. We just need to know if it actually does show up as the output for some vector x. And if it does, what vector x would that be? What does t map to 7, 1? Well, to answer that, what we need to do is see if we can find a solution to this matrix times x equals 7, 1. Now to find the solution to that, you know that well, we've solved problems like this before. The simplest way to do it is maybe to form an augmented matrix using the coefficient matrix here on the right-hand side. So if we form the augmented matrix there and try to solve for x, we could row reduce it. If you do, the reduced echelon form looks like this. And as you take a look at this, this tells us that x1 is minus 7/8 x3 plus 1, and x2 is equal to minus 11/16 x3 minus 1. Now the point is we needed to find values for x, and x is supposed to be from R3, so it's supposed to have x1, x2, and x3. And we have that. we know what x1 is in terms of x3, we know what x2 is, and we know that x3 is a free variable. So the answer is yes, 7, 1 actually will show up in the range. There is a solution to this matrix equation. And in particular, if we were to kind of take our reduced echelon form and rewrite it in parametric vector form, we know that the solution x would be this 1 minus 1, 0, plus x3 times minus 7/8, minus 11/16, and 1. Remember, the free variable x3 gives you a parameter in the parametric vector form. Okay, well, that's all we need to do for this first video. We have defined a matrix transformation, function, mapping, domain, codomain, image, range, and matrix transformation. We have talked about the images of a given point under a given matrix transformation. That's just what happens when you plug a vector into the matrix transformation. And we've talked about finding whether a point is in the range or not in that last example we saw. If you have any questions, please let me know. Otherwise, I'll see you at the next